Alright, so I'll get started on the next section now. Alright, so we'll go through thermal analysis now, and then there's some workshops that we'll do. Okay, so just a quick agenda. So we cover linear thermal, and then there's sort of drawing the analogy of temperatures to other physics, and also contact in the context of thermal analysis, and then also phase change, and linking a thermal solution to a structural solution. Okay, so when a model is considered linear in thermal, the boundary conditions are not temperature dependent. So that means that things like convection coefficients don't change appreciably with temperature. So material properties also don't change with temperature. So with some materials, they can have highly non-linear relationships between thermal conductivity and temperature within the body. So if a body has a huge temperature variation to it, the local thermal conductivity will change throughout the body. So with a structural simulation, we have this concept of a stiffness matrix. So that's based off mostly based off displacements. So in a thermal model, this K matrix is effectively it's called the conductivity matrix. So because we're basically solving a conductivity problem in a thermal simulation. Okay, so when we had for a structural simulation Kx equals F, where X is a displacement, so for a thermal simulation it's a temperature. So here our K or our conductivity, so here it's as a function of temperature, so it can be temperature dependent. And then our Q is basically our heat flow. That can also be a function of temperature. So you can think of this as a force that could vary with the amount of displacement or temperature your structure is undergoing. Okay, so when this is done as linear, there's no temperature dependence of the conductivity matrix or the heat flow. Okay, so if we draw the analogy between the two equations, so for a thermal we don't have there's no equivalent of mass per se, so in terms of damping, so for a thermal analysis that's like a heat capacity, because it's basically storing heat energy. So if you equate the different quantities, so displacement is temperature, force is heat flow, so pressure is like a force per unit area, so that's a heat flux. So the things that you get out, so strain and stress, so these are thermal gradients and heat flux. And then when we look at reactions from a thermal analysis, we're basically looking at reaction heat flows. So if you specify a temperature on a surface, that's like saying you're applying a displacement. So to maintain that temperature, you need to apply a certain amount of heat flow. So it could either be that you have to remove a certain amount of heat, or you have to apply a certain amount of heat to maintain that temperature. So in a lot of thermal simulations that we do, we often apply a temperature as a simplification. So it might be for an infinite heat source or an infinite heat sink, and then based on whether or not we can supply that much heat, then that will dictate whether or not that constant temperature assumption is valid. Okay, so with thermal models for very simple cases, they can be solved analytically. So we can use a voltage drop analogy. So you can convert a heat transfer coefficient or a conductivity into an equivalent resistance, basically. So you'll have two known temperatures normally. If you've got a temperature, say, of still air on one side and temperature of something else on the other. So you might have water flowing through a copper pipe, and then there's ambient air on the outside, the temperature of which you know, and the fluid flowing on the inside, you know that temperature as well. So if we look at it as just if you treat it just as a simple plain wall, so if we ignore the fins, so here we've got still air on the inside, or this might be water flowing at a certain velocity. So we can calculate a heat transfer coefficient. So we've got a wall of a known thickness, and we have a certain conductivity, or a K value. So this will vary depending on the material. Okay, and then you've got air on the outside. So it might be fast flowing air, sort of at a low temperature. So here this is basically a simplification of a inside air in the room, and then we've got a brick or a steel wall, both of the same thickness, and a very cold exterior. So what we're aiming to do is find the temperature of the inside wall. So you obviously don't want it to be too cold, because then if you go and lean against it or put your hand against it, it will be might be either too cold or way too cold. So you don't want it to be below freezing, because then you'll get condensation on the inside wall. Okay, so if we start doing our thermal resistance network, so these are basically like resistors in an electrical network. So there'll be a certain voltage drop or temperature drop across each of these thermal resistances. So this first thermal resistance here is basically our convection boundary layer on the inside wall. The second thermal resistance is basically the conduction path through that wall. And then the third thermal resistance is basically our outside convection boundary layer. So if we look at the R2 value, so depending on whether it's brick or steel, you can see there's a huge difference in the thermal resistance. So basically, the higher the thermal resistance, the greater the temperature drop across the particular resistance. So here we want the temperature drop to be as high as possible. So we want this R2 to be quite high relative to the other thermal resistances. So if we do some quick hand calculations, so the most important thing is that the heat flow will depend on the total thermal resistance. So because these two temperatures are fixed, there'll be a certain heat flow across that entire thermal resistance network that will change based off that total. So the only variable here is this R2, and then the relative temperature drop across those three resistances is the same in the same scale as the resistances themselves. Okay, so for a steel wall, there's a lot more heat being extracted by the outside air. So if we look at the temperature drops, so for a brick wall, so we've got 11 degrees on the inside air, 18 degrees through the wall, and then 0.4 on the outside boundary layer. So if we have a steel wall, on the inside we get a 28.5 degree temperature drop. Across the wall, it's hardly anything, and on the outside it's 2 times hardly anything. So the important part here is that the 28.48 degree temperature drop means it will have a negative temperature on the inside wall. So in order to get the same insulating effect from the steel, it needs to be just over 33 metres thick. So because steel is such a good conductor, that's obviously not a very good insulator. Okay, so if we do a simulation of this, so I'll show you this model in a few minutes. So you can see the temperature gradient across the wall. So the colours are the same, but if you look at the temperatures, so you can see that this one goes from -8 to or -8.4 to -8.9, whereas on the brick wall it's +8 to -9. So there's a huge temperature drop across there. Okay, so I'll just quickly show that model. Okay, so here I've got both of the models side by side. So there's a material assignment of brick for the bottom wall, and then the top wall is just cast iron. Okay, so when we apply our thermal conditions, so here I've got inside air, so let me just switch my units. So we've got a convection coefficient and then a temperature. So the ambient temperature is what this wall is convecting to. So depending on the temperature of that wall, that will either lose heat or gain heat. So it's going to depend on what's going on the other side of this wall. Okay, so if I look at the inside air, so it's the same condition applied to the other wall. Okay, so for the outside air, so we've got a convection coefficient and then the temperature that that's convecting to. So here this is at -10 degrees. Okay, so if we look at the temperature, so that's the same scale. So you can see that the top one, which is the steel wall, there's hardly any temperature change through that wall, whereas on the bottom one there's quite a lot of change. So it's basically the whole spectrum of that contour there. Okay, so if we drag and drop the convection conditions, I'll do inside air 1, outside air 1, and then I'll evaluate the results. So these should be, one will be a positive, one will be a negative. So the positive is saying that there's 44 watts going into the face of that wall, and the negative is saying there's 44 watts being removed from that wall. So that makes sense. So we're removing heat to the cold side, and the heat is being added from the ambient air to the wall. Okay, so here this is you can very easily verify this with a hand calculation. Okay, but real models aren't always that simple. Otherwise there'd be no need for us to do a simulation. Okay, so there's not very many boundary conditions in a thermal model. So all we're doing is solving for the temperatures at each node. So you really only have heat flow and heat flux. So heat flow is a specified heat energy, whereas heat flux is a per unit area. So we can also have an internal heat generation. So you might have a sort of a volume or some sort of device that's generating heat energy. So you can do that as basically as a volume generating heat. Okay, so you can have an enforced temperature. So this might be coming about because you've got a heat source or a heat sink. So it might be that you've got, say, refrigerant at a certain temperature. So that generally won't change temperature if it's undergoing phase change. So you normally assume that's a constant temperature. So with a convection, so our T ambient is specified. Our surface temperature will quite likely vary across the surface as the solution is progressing, or it might just be that there's a temperature variation across the surface because it won't be a constant. Your conduction path might not be a constant value everywhere. So it's highly likely that this heat transfer coefficient, the heat that is removed locally at each part of the face will vary because this T surface minus T ambient is varying. Okay, so radiation. So this is another heat transfer mechanism. So it's only really significant when there's a large difference in surface temperature to the ambient. So because this sigma term here, so this is a constant, so it's from memory 5.67 E minus 8, and then this emissivity value is normally somewhere between 0 and 1, so that will depend on whether it's a black body or if it's a reflector. So radiation effects only really start becoming significant when you have temperature differences of a couple of 100 degrees. So if it's below that, it's usually something you can ignore. So the reason why we tend to ignore it for low temperature differences is that it makes the model nonlinear, because this is a t to the 4th power. So this will vary significantly based on the temperature differences. Okay, so conduction, you don't need to specify that as a condition. So it will be a natural property of the body. So unlike a convection where that has to be applied, even though you've got air, you might have air modelled. You generally don't do that. You model it with a convection condition. So there might be a conduction path through the air, but that's not going to be as dominant as the convection. Okay, so any face you don't apply a condition to will be assumed to be perfectly insulated. So if you're looking at something that might have, say, a symmetry condition on it, if you don't apply any conditions on there, it will behave as if it's a symmetry boundary condition. So you still can apply a perfectly insulated condition, so then when you do plots, it actually shows up as a condition. Okay, so there is a way of simulating cooling channels in devices. So you might have, say, a steel block with cooling channels running through it. So rather than doing this as a CFD simulation to find out the heat transfer coefficients, you can sort of, I wouldn't say dumb down, that's the wrong word, but you can simplify your model by assuming that the heat transfer coefficient on the channel is a constant value, and then the temperature of the fluid flowing through it, you can model that temperature change. So in this model here, so this is basically a steel block. So let me just do a cut through this block. Okay, so on the inside of this block, there's basically a cooling channel that sort of loops through, and then there's another line element which is basically assigned properties of a cooling fluid, and then we assign a temperature at the inlet and then a mass flow, and then from that it's able to calculate the heat that's picked up by the fluid that's flowing through here based off its properties, and also the heat transfer coefficient on the wall. Okay, so here this is a slightly different model. So there's 3 cooling channels with a certain flow rate and a given inlet condition, and then there's a heat flow being applied to the outer surface. So this will, in this case, it's actually heating up the fluid that's flowing through there. So if I want to try and keep the temperature change as low as possible on that fluid, I would either increase the flow rate or increase the heat transfer coefficient on the internal channels. So you could do a CFD analysis to get a better idea of what that heat transfer coefficient will be, but because it's a fairly simple flow channel, it's not changing cross section or anything like that, you can normally do some fairly detailed calculations based off Reynolds number and different non-dimensional numbers to come up with a coefficient. So I actually did that as an exercise for this particular model, and using a CFD-based convection coefficient, which varies slightly along the length, versus something that I did with hand calculations, the values came out to be pretty much the same for the heat transfer coefficients. So there's no time wasted in doing a CFD simulation because it's not really warranted for such a simple flow condition. Okay, so here this is showing some of the results that we can get. So you can get the temperature along the line, which is basically the temperature of the fluid stream, and then you can see the temperature along the wall of that fluid stream as well. So there'll be some sort of temperature rise or drop across that fluid boundary layer. So you can sort of semi-simulate that, because I mean the important things we need to know are the temperatures of the solid and the temperatures of the fluid. So you can simulate those quite readily. Okay, so if you're modelling assemblies and they're in contact, so we have this concept of this pinball region. So if there's small gaps in your model that aren't really there, they're just there because of the mesh, you want there to be heat transfer across parts where it's not physically touching. So this pinball controls how big a gap you allow before you don't allow conduction to take place. So here this pinball radius is shown by that sort of gap there. So where there's green solid lines and the faces aren't touching, there is heat transfer across that gap. So where there's green lines that are dotted, there's no heat transfer taking place across those faces. Okay, so we sometimes need to use this in order to not have to go back and modify the geometry. So sometimes we might have gaps that are there just because of the way we've modelled in CAD. Okay, so usually for most cases there will be some sort of temperature drop across an interface. So in most cases we want this temperature drop to be negligible, but sometimes we might need to, that might be a characteristic that we need to include. So within a contact there's a property called the thermal contact conductance. So this is basically almost like an additional thermal resistance across an interface where you get a temperature drop because of that interface. So it could be that you've got, say, trapped oxides, or it might be a fouling or a corrosion on, say, two steel parts, and that's interfering with the perfect conduction path. So this value can be fine-tuned, and because this is something you can physically characterise or measure, it's a value you can actually assign a meaningful physical value to. So if you're doing if you've got experimental results and you've got thermocouples and you're measuring temperatures at two different places and there's a contact in between, if your results don't match, it's highly likely that your thermal conductance value that the solver uses is assuming, because it normally assumes a perfect conduction. You don't actually have perfect conduction going on in your model, so you can use this value to adjust or account for that difference. Okay, so in terms of a model becoming non-linear in thermal, so any property that's not constant with temperature, so thermal conductivity is a typical one for some materials. If you've got any boundary conditions that have a temperature variation, so you can have temperature dependent convection conditions that might vary based off different things like the surface temperature, or it might be higher for a different ambient temperature. So they need to be accounted for by making the model non-linear. So radiation, so because it's T to the 4th power, and if you want to simulate phase change as well. So you can actually simulate phase change in a material by entering a temperature enthalpy curve. So there's a workshop that we can do that sort of demonstrates that. Okay, so phase change, as well as being nonlinear, it's inherently transient because it will happen over a time, and we need to simulate real time. So just like we had quasi-static versus transient, there's similar sorts of considerations for thermal. So phase change has to be done as transient. There's no way of getting around that. Okay, so with time step control, so for a structural simulation, it was based off natural frequencies. So with thermal problems, it's based off resolving temperature gradients, both in time and space. Okay, so if we look at so this green line is normally unknown ahead of time, and we need to capture that temperature change with certain time steps. So we need to make sure that this temperature change across the time steps isn't too severe, because if your thermal conditions are changing based off temperature, you don't want those conditions to change too much, because you're basically linearizing the behaviour across this time step. So if you linearize too much of a change, then your solution is going to be both inaccurate and it will quite likely be unstable in solving. Okay, so thermal nonlinearities can be a little bit more challenging to solve, because if your time step is too small, you can get oscillations in your temperature, and you can even get negative temperatures, which are physically meaningless. So I've seen cases where people have had time steps that are way too small because they're trying to resolve large gradients, but they've gone too small, and there's plus minus 100 degrees across one element, which is not physically possible. Okay, so if your time step is too large, then you don't capture the gradients accurately. So both of these conditions are possible to it's possible to sort of get yourself into these situations. Okay, so I won't dwell on this too much, but there's basically two non-dimensional numbers that you can use to basically estimate what your time step size is. So one of them is it's a dimensionless number that relates the convection to the conduction, or the thermal resistances. So you need to use this number in combination with the Fourier number, which is it's related to time, and it's basically heat storage versus heat conduction. So it's more for transients or conditions. Okay, so there's some guidelines down here on which number to use to calculate your time step. So normally, if you give the solver a range of time steps to use, if that time step range is big enough, then you generally don't need to worry too much about sort of going and calculating what these values need to be. Okay, so when we have phase change, so this property normally isn't there by default. So it's normally something you need to manually calculate. So when we have a phase change, there'll be a latent heat. So this is the heat that's required to basically change the phase without changing the temperature. Because when there's phase change, there should be no temperature change occurring, unless it's a sort of a more complicated material where you've got multiple phases. But we'll just keep keep the explanation simple and just have something with one sort of phase transition. So if you've got ice at 0 degrees, so to melt it, it won't change temperature until it's all changed to water, and then the water will start changing temperature. So the same thing happens when you transition from water to steam. So okay, so a typical curve will have some sort of transition. So this solid and liquid temperature, or it's basically a transition between two phases. So we generally try and make this transition phase a finite temperature range. So, I mean, in theory, it's essentially 0 for something like water, because here we're basically saying that there's a phase transition from solid to liquid where the temperature is changing rather than it being a step change. Okay, so any applications that involve phase change, so again, solidification or melting. So if you're simulating, say, a casting, where you're having a metal change phase from liquid to solid, so you want to make sure that you don't get any sort of chunks that are all solid before everywhere else. So you don't want to have sort of parts of your device that you're solidifying, sort of freezing and trapping all the liquid underneath, because it needs to expand or contract, and that will cause all sorts of problems in your casting. Okay, so one of the things we'll do is a flywheel casting simulation. Okay, so most of the time we will, even if we're just considering just simple temperatures, so we'll want to calculate what the stresses are from that imposed temperature field. So if you've got differences in temperatures in your assembly or structure, that could cause expansions or contractions that will lead to high stresses. So you can impose mechanical loads on top of thermal loads, and if your temperatures are non-uniform, you can't just apply a constant temperature to your parts. You have to calculate that separately. So because your thermal deformations don't really affect your structural loads, you can calculate them separately. So this is what we call a sequential coupled thermal structural simulation, because these two physics, if you like, don't interact with each other, or certainly not in a coupled way. Okay, so we basically link our thermal solution to our structural setup. So here you can see this with the analysis system link, and then you just apply your structural loads, and then you can calculate your structural displacements that come from mechanical loads and thermal temperature differences. Okay, so it is possible to have both of these physics solved together. So this is what we call a direct coupled field analysis, or in this case it's structural thermal, and they're basically solved together. So the assumption here is that the displacements are a function of temperature, and the temperatures are a function of the displacements. So this effect typically only happens when you've got devices that are of the micrometer scale. So here, this scale here is 3e minus 5 meters. So things that are referred to as MEMS, or micro electromechanical structures, are devices that typically have this sort of effect. So a lot of force transducers employ this sort of thing. So you apply a voltage, and then there's a displacement, and then that displacement is used as a pre-stress. And then if you apply a cyclic voltage, that will have a cyclic displacement, and because they're both transient in nature, they both interact very in a very tightly coupled way. Okay, so you generally don't employ this direct coupled analysis for sort of larger structures, because if you make one physics transient, they both have to be transient. And it's very expensive to solve a structural model for transients, because you're solving for a lot more degrees of freedom. So it's not as expensive for a thermal analysis, but the other side of the coin is that your time step is governed by the physics with the smaller time step. So you can get into the situation where you have a structural model. Time step is dictated by the frequencies you want. That time step is too small, it results in temperature oscillations in your thermal analysis. So that generally won't happen for a MEMS type device, but if you did try and simulate both of these physics at once in a larger structure, it's highly likely that you'll run into that scenario where your structural time step is too small for a stable thermal solution. So it's sort of, that situation sort of takes care of itself, because you don't need to do it. Okay, so if you're coupling between a transient and a thermal, so this is just what I was explaining, you don't need to do the structural as a transient. So if you've done a thermal transient, you can take your temperatures at discrete points in time and solve that as a quasi-static solution. So because the two physics aren't linked, they can be run totally independently. So all you've got to worry about in your structural solution is that your temperature history is properly accounted for. So if in your thermal simulation you're simulating over, let's say, 30 minutes, if it's a transient right in the beginning, your temperature gradients are quite large. When I say temperature gradients, I mean temperature versus time. So you have a lot more time points captured in that initial time. And then as you're sort of having lower temperature gradients, you can space your time points further out. Okay, so this is just reiterating with sort of direct coupled. So it's usually only tiny structures, and I'm talking tiny, sort of fractions of a millimetre. So unless you're doing sort of MEMS type devices or sort of micro machines, you generally won't need to do a fully coupled solution.